Good evening. We are happy to have with us today another ex-physicist who turned into a machine learning person, Michal Rosen-Zvi. She's actually the academic granddaughter of Chaim. She did her PhD with Ido Kanter at Bar-Ilan, actually working on statistical physics of learning. I know what she did. And then moved through a lot of interesting places and people, through Michael Jordan in Berkeley, and then Fort Smith, and so on. You got the name of the people in Ireland, Max Sperling, Pierre Bldg, and a few others, and then came back as an expert to machine learning. Spent a few years here as a postdoc in Jerusalem, working with Yair and with me. Then moved to IBM research in Israel and Haifa, and very quickly became the head of the machine learning group there. And he's now managing, actually, I don't know how many people, a lot of projects. So we are very happy to hear about your new stuff.
Thank you very much for the introduction, and thank you very much for inviting me. I'm very happy to be here. Actually, I remember, I think it was 7 years ago that I sat in this, I don't think it was the same place, but I was here when Yair gave a talk about Bayesian models and other things that he does with vision. And it feels nice to come back and to talk about what I do and my team do in using Bayesian networks in order to analyze text. And I'd like to use around 15 minutes to describe what we do, and I can tell you what I'm going to share with you and what I'm not going to share with you. So I'm going to share with you the approach to machine learning, the approach or the method to analyze text using machine learning. I'm not going to tell you how people from cognitive science are using this in order to interpret the way people are looking at text and using text or thinking with the text. I can mention that I worked with Mark Steyvers and Josh Tenenbaum and other people who are using the same models that I'm going to share with you today in order to interpret the way our mind works. But because I don't know much about it, I'm not going to talk about it. I can give you one example just to give you the taste and the motivation for this work. I've read about an experiment that was carried out in one of the Ivy League universities in the US, and I don't recall the full details, but the point was that people were asked to construct sentences from distinct words. And they had a list of words, like the first list of words contained Arizona and sun and going and playing and all kinds of words, and it was different sentences. And particularly in this experiment, in each sentence there was something that reminds them about elderly people. So either it's the place where they go for pension, or it's playing what they say, these elderly people in the US, it was playing, I don't know what you call it, bridge or something like that. And then there was being old and being tired. And then they monitored how long did it take to these people, and these people were not aware of it. How long does it take them to go from the room where they entered for doing this test to the other side where the stairs were? And it took them, those people who carried out the test containing the words about other people, it took them much longer to walk after they did the test comparing to what they do before they take the test. So I think that not in the deliberate way, we use it many times. Actually, I only thought about it when I attended my yoga class, and there's all kinds of animals that we need to compare or repeat or whatever. And at the end, always at the end, the teacher tells us, okay, now we are going to move to happy baby. And we have some kind of a posture that imitates the happy baby. And I always end this class very happy. And only after reading this experiment, it makes sense that maybe it also triggers something in my mind. But in any event, the whole story that I'm going to say here is about the concepts that are behind the text and how can we use them in order to analyze text. And I'm going to use Bayesian models, and the paradigm in this approach is that we would like to be able to predict things. So it's not to understand the mind, but how we can use some understanding of the way we look at text in order to be able to predict later on what will be written in a paper or something like that. So this is the story, and I'm going to cover some work that I've carried out with many collaborators. I'll mention at the end all the people, so in the middle I'm not going to focus on who did what, just on the story itself. So modeling text in general will be the first part, and generative models in a nutshell, what does it mean? Then LDA, Latent Dirichlet Allocation, a model that has been proposed by Blei, Andrew Young, I don't know how to pronounce his name, and Michael Jordan, and they did it in 2003, and it triggered a lot of work around this model, and some of the work that I'm going to talk about is around this model, but I need first to introduce that model. So the other work is the orthotopic model and the latent topic for hypertext. I'm going to talk about it. Of course, nothing is really revolutionary new. So I'm looking at Tali, and I remember that when I came to do my postdoc, and I talked with you about LDA, and you always told me, okay, but we did similar things in this way and that way, and of course there are many prior works by Tali and others that are relevant to the way to the LDA, but I'm going to use this as my starting point, even though we know that there are prior works. I'm not assuming anything. I'm starting from the very beginning, and I'm starting from one way to model text in a mathematical way. And in this way, we are going to talk about words in documents. And a word will be treated as an idea, as a number in the document. You have a vocabulary. Let's say that you use a vocabulary of size of 5,000 words. So each word has a number in one of these numbers between 1 to 5,000. So this is the way to represent a word. And a document, again, you have a collection of documents, and each document can be represented by one of these numbers between the size of the collection of the document. So if you have 100 documents, you have 1 to 100 IDs for the document, and you have these words. And now you want to represent...
So each document is the vector.
Yeah, now I'm going to move to the vector, but first... here, sorry. Yeah, you're right. I mixed between another Apache one. Sorry, again, you're totally right. Thank you for Professor Sokolinski. So I was confusing between the cochrane metrics that I'm going to talk in a few slides ahead. Forget what I said about the documents. We are only talking about words, and these words are IDs in this vocabulary. And now when we want to represent a document in a world that contains words, we can indeed define a set of a reference set or some axis that represents the different words. And the document will be how many times, will be a vector that represents how many times each word appears. So if we have a vocabulary of 3 words, the document, if it contains twice the third word, and once the first word and nothing from the second word, that will be the vector of the document. So this is what is called a feature space, and it's one way to represent. I'm going later on to talk about another way. This was my confusion, and I apologize. But in this story, we have this way to represent different documents. And now, if we want to compare between documents and to estimate if they are close or far away, we can ask what is the angle between the different documents, and if they contain many similar words, they will be very close by. Clearly, when you want to talk about documents and you are interested in the content of the document, you don't want to be bothered by the different words that has nothing to do with content, like words of is, are, maybe like, because like is like what I just said. So all kinds of words that sometimes people are calling them stopping words. These words are removed because they are going just to disturb us in analyzing the relevance of one document to another. And so this slide shows you the motivation of doing content-based. What do I have here? Pointer. Thank you. So, as I said, bag of words is a way to represent the document when we ignore the order of the words in the document. So this is why it's bag of words. And we have a word space as I showed you here. And in many occasions, we have a larger vocabulary than the number of documents that we are looking at and trying to analyze. So if you look at the collection, say, of papers submitted to a conference in the last 20 years, say you have the NIPS conference every year, and you look at the number of papers, wow. So I know that there are around 3,000, maybe 4,000 now of papers that are digitally available, I think since '87, and clearly there are many more words in this, if you look at the vocabulary used, thanks to the language, we have many more words that we can use in order to represent what we would like to say. And now, what can you do when you have a collection of documents? What would you like to do? What are the applications that you are seeking, and the reason people are modeling these documents in this way? One clear application is retrieval. In Google, you seek for something, you put a query, you would like to retrieve the relevant document. So you would like to know something about the connection between the different documents. And this representation is one way to connect between documents. So this is one of the motivation of representing documents in this kind of space and trying to retrieve the content. It's the actual number, so these are integers. They just count the number of occurrences. So what kind of normalization are you interested in? So we are going to, you are absolutely correct, and there are many ways for normalizations. I didn't talk about them here, so I'm going to talk about a probabilistic model, and then it will have totally different representation. But when classic information retrieval people are looking at this feature space and trying to analyze it, to represent the document and do retrieval, they normalize it by the logarithm of the occurrences of the document, or the inverse occurrences of the document and the inverse occurrences of the word, in order to calculate how clear a document A is document C. They want to take into account the occurrences of the words in general in the document and many other things. So there are normalizations, of course, in order to make it more efficient and a better representation. But I'm not going to get into this direction, because the direction I'm going to go to work with and to show you, and it's more like some kind of a religion. If we believe we can understand how these documents were created, we have some model of the probabilistic understanding of how a document is generated, and then the whole story is compact into this approach, and you have everything, the normalization, everything is integrated into the approach that I'm going to show. So this was just only to give you the first taste of what you can do with documents, how you represent them, and what you would like to apply with them. But I'm not going to focus on that. So this is something I think it's clear that when you think about words, it's not obvious what's the connection between words. I mean, nowadays we have word nets, so we have many people who did some connections between words. We have Wikipedia, where you have these categories that people are putting, so you have some connections between concepts, but there is no obvious way to do it. So you'd like a mathematical way to construct it. Of course, it's high-dimensional, and there are many tasks that you'd like to carry out, and you would like to address this high-dimensional representation. And I think, when I gave these kind of talks, like, I think it was 10 years ago, maybe less, when I was in Irvine. No, it's less. It's 8 years ago. So when I tried to motivate and say, okay, the cost of the digital storage are dropping, it was like some interesting news. But now it's no-brainer. It's clear that you can store whatever you want, and there are large and piles of documents, and the task is to address them. And one of the examples that we did later is applying our methods to the Enron collection of emails. I don't know if someone here recalls, maybe the people, some of them are too young to recall the story of this company, Enron, that was doing some monkey business, and people were catching them, and then all the emails were uploaded, scanned. They didn't agree to provide a digital record of the emails, but everything was printed and then scanned and then stored in the available collections. And people like us who are doing machine learning use them as toys in order to analyze their text and see interesting connections. Like everybody there is talking about vacations and some connections to the White House, many interesting things, maybe also some kind of other things that maybe it's not okay to share, like interrelationships between men and women that they had there. Everything can be revealed automatically by using these kind of things, because now we can store everything and download everything.
You're talking about cheap or cheap?
Yeah, sorry. the chips, the computer machine chips, IBM chips that can store that are. I don't know the right spelling. Is the correct one? Is the correct one? Okay. But let's go. הצ'יפים הם מאוד זולים. הצ'יפים הם מאוד זולים.
Chips are cheap.
Yeah, I'm saying it's מאוד זולים.
No,
I apologize.
Okay.
But let's move on because
Okay.
the main story here is how we use Bayesian models in order to analyze text. So I want to give you a very brief introduction, and I guess it's very hard in this kind of talk, and everybody has different backgrounds. So I'm going to start very, very slow, and just let me know if all of you are very bored. I'll skip it. But I need to give something to start with, and the something to start with is let's say that we have a set of documents that are labeled, meaning each document has some kind of a category. This document is about family, and this document is about work, and this document is about fun. You have different categories for each document, and now we represent the set of words in the document with a vector that contains the ideas of this vocabulary. And we have, for each document, so the index D represents what document we look at. And for the first document, you have category CD, C1, for the second C2, and so on, and you have a set of words in each document. And again, we are talking about bag of words, although later on we did some work that takes into account the order of words, and of course there's a lot of information in the way the words are ordered. But in this case, still I'm talking about a set of words that are put in some vector. It's not the feature space of before. It's just a vector that says in this document you have 2 words with ID 6, 7 words with ID 8, and so on. And it's represented in some vector. The length of the vector is the number of words in this document. It tells you the first entry is the first word, the second is the second word, but the order doesn't mean anything. Do you take into consideration if the words are similar to each other? In this, that's the aim. The aim is to find out, you're talking about synonyms or taking about, yeah. So the aim at the end is to infer the connections between the words, to infer similarity. And what I presented in the 2 slides before was one way to do it, which is the feature space and so on. Now I'm going to get into the main talk and to say Bayesian models that infer relations between words using some generative model. That's the story. So just the right question at the right time.
Okay, between words, not between documents.
Later on we can do it between documents, we can do a lot of things. As I said, it's religion, we can do many, many things. It's everything. When you try to analyze text, of course. Nothing beyond it. Classes are mutually exclusive. Okay, at this stage. So let's say that, and now I'm talking about a Bayesian model, and you have here nodes. The nodes represent random variables, and the arrows represent connections. And actually, you can think about joint probability distribution when you look about condition distribution. And this representation immediately tells me that these 4 random variables are conditionally dependent on this father or this parent in the tree. So we can look at this in a Bayesian model. When we see this kind of a picture, it means that we have a joint probability of 4 random variables, and of 5 random variables, and 4 of them depend on the first one. And given this category, each word is independent. They are not dependent of each other. These are this tree tells me all this story, and this is a compact way to represent the probabilistic relations between the random variables.
What is 1? What is index 1?
Just tells you that this is the first document, and
this probability are all the documents.
So there are, here we have 5 random variables, and we have random variable for the first. I'm here representing only the first document. This is the first document. It contains 4 words.
But you have a generative model for each document?
Yes. It's very similar.
Category, but
it is very similar. It's the same one, so there's a compact way to represent it. But
essentially it's a category, it's not a document. C equals A, this is...
Yes, but our assumption is that each document has one... Each document has one category. So let me explain in 2 sentences, then if you still have questions, I'll repeat it, because I think I didn't do it the right way. So let me start from the beginning. So the assumption of how a model is, a document is generated is as follows. First, you pick the category. Given the category, you pick a random word in the document. And in this way, a document is created. And in this model, the assumption is that given the category, there's a probability distribution for each word. Say that for category A, the word pet is very likely, the word dog is likely, milk is very likely, cat is likely, but the word food is not very likely, and dry is not very likely. So there is a vocabulary, and you have a probability for the full set of words in the vocabulary. And given a category, you have some probabilities. So this is the model. It's a very simple model. And the reason that you have color here, blue, it's not because IBM is the big blue. That's one reason. But the other reason is because when we represent Bayesian models, what disturbs now? Okay. So we have when we have Bayesian models, typically when the node is shaded, it means that it's observed. So in this model, we assume that when we see a document, we also see the category. So we see that there are 4 words. We see that the category is 8, and we now assume some relations between all the observed variables.
I'm sorry, I still don't understand your notation. What is CP? P equals P. I don't understand. You have how many categories you have?
No, here you are absolutely right. This is a typo. This is a typo.
Okay,
you have 1 to D large D document, so this should be capital D, and then it should be equal 1 to number of categories. So 1 of these. You are absolutely right. This is a typo. I apologize, and you are the first one to say that. So as you can see here, I used it last year in a visit in Boston, and nobody commented on it. So I appreciate your.
So these are the empirical probabilities for this document, or these are the probabilities of the category?
So it's the probability for words in a document where you assume that the probability is drawn from the category. So you assume that first you pick a category, then you pick the words. And this is an assumption of how words are created in a document. So say someone here wants to write a paper, so they say, okay, this paper is going to be about neuroscience. Let's say it's very narrow field, but I don't know. This paper, maybe this is some news article. This is something for the media. We are going to talk about neuroscience. And now when you decide neuroscience, you have different likelihoods for different words, and you pick them. Later on, and we don't address this question, later on you order them in some ways. This has to do with the syntactic rules. We don't address this. But the question, what words do you pick? You pick them from this distribution. And if you assume this, you can infer these probabilities, of course. So this is a pure mathematical exercise. If you assume a model that we call this multinomial distribution, you assume that given each category you have some probability between 0 to 1 for each word. And then you can just infer what are the probabilities given each category. And if you see a lot of documents with a lot of different categories, you can, for each category, you can say what is the most likely probability of words given category. Is this clear? So this is the easy part. So if you have any question here, that's the right time, because in a minute you might lose me. So, okay.
So the length of the document. So this is what you call a generative model. We're not yet there.
Yes, that's a generative model.
So
it's a very simple one.
I want to generate my article.
Yes.
Okay. So I have a probability of.
So it's Bayesian. Typically, you have some prior for the categories.
Right, so
it's you, so you might talk about
animals.
Yeah. Okay.
So now how many times I sample?
That's your. So in some of the models, this is part of the model, the decision of how many words to do. It's also drawn from a random variable. It's also a random variable, and it's drawn from probability. But here, I assume that you know in advance. The author, the journal told you use 1,000 words, and now you just pick them from the category. And this is one of the very simplest generative models. And this is an easy picture for you to understand what I'm going to talk about. And now this is a compact way to represent the same story, and I hope there are no typos here. So here we assume that now the place represents repetition. So if we do the same drawing again and again, we don't need to do it all over here and then get some typos. We can just do it once. And that's what you have here. You have D times a selection if you have D documents. You have D times a selection of random variables, which is the category. And then for each random variable, you pick at random the word. And you do this ND times, where ND is the number of words in each document. It's given in advance. It's not part of the model. That's why it's not in a node. I mean, everything is a node. It's a random variable. relations are here, and if it's shaded, it means it's observed. That's the story. It's a very simple story. And then the probability for a word W given a topic Z is some variable multinomial, theta WZ. It's a probability for the word W given the topic Z. And given topic here, so there is some typo. Topic here is the category, because in a minute it's not going to be observed, and I'm going to switch to a different letter. So sorry for the confusion, but this is the standard way in the literature it appears. So that when the category is observed in C, in a minute it's going to be Z. Okay? What very silent? So that's a good question. And actually, the large part of what I'm going to talk about in the LDA is to assume something about this distribution, about theta. And that might help you in better inferring the... Here we don't assume anything, we just infer it. If you assume something in the religion of Bayesian networks, it means that it's a random variable and there's some probability, and we're going to do that. We are going to address this research. So here is we talk about probability, so I'm going to skip the rest of the equations in this presentation. There are many of them, but I'm just going to go through these equations just to give you a taste of what is this mutual probability distribution. We have for a product over all the documents. Per document we pick at random the category, and then per word n in each document we pick at random the word from the category and the variable theta that defines the probability. So this is the mathematical way to represent this story. So now we are going to talk about a more complex model. This is the LDA model, and here the assumption is somewhat more advanced. You assume that each document that you're going to write contains a set of topics, and the assumption is that it a priori can contain all the topics in the world. So, or all the topics if we analyze a collection of documents submitted to a particular conference. So there's a set of topics relevant to this conference. And when you run the document, you just pick a probability over the topics from this set of topics. So you might talk very little about fMRI and a lot about monkeys and something about hearing. Let's say these are the three topics in this conference. So theta is a vector. It sums up to 1, and it goes over all the possible topics. Now we talk about 3 topics. It was fMRI, hearing, and I forgot the third one. Monkeys. Because I thought about some people who I know are doing neuroscience, and so these are the 3. Not about the people, about the science, but these are the 3 possible topics. So you have probability. You might have 0.1 for fMRI, 0.8 for monkeys, and another 0.1 for. Given the probability over the topics, you pick at random a topic. And now when you want to write a document, you first define what is the distribution over the different topics. Then you pick at random a topic, and given the topic, you pick a word. And then you repeat it. You pick at random another topic. Given the topic, you pick it a word. But the selection of words is now again from this multinomial, but you assume something, and this has to do with the question you asked before. You assume something about how you pick these multinomials. I mean, maybe this probability has to be very narrow, very shallow, sparse, not sparse. So you have some prior, and in order to have the mathematical work well, this is the Dirichlet prior, and this is the multinomial, so they are conjugate, and there are some mathematical relations, and it works very well when you want to infer from the observed data what are the hidden variables. So actually, I mean, given the limitation of time and how much time I spent in the introduction, I don't think that I will go much further more than that. So let's focus on that for a minute and understand the concept and what does it mean, and then I'll just show you how you apply this in many ways. But the story here is as follows. Each node represents a random variable. If you don't see the random variable, if it's not shaded, it means that it's a latent variable. You don't actually observe the value. So as before, you only observe the words. This is what you observe. You observe the words in the document. But now you assume a much more complex structure, what happens below it. And there are people, as I said, like Josh Tenenbaum and Mark Steyvers and others that I don't know, but I know on the field too, who are using these kind of models to infer what we think about when we think about different words. Because this, you have some more complex understanding. And in my mind, it might be related to, one way to prove that we think in concepts and then pick words is this Hebrew game when you ask about the color of this table, and then you ask about the color here, and you ask about other white colors, and then you ask what does the cow drink, and just try to translate it in your head, and then answer the answer, and then you can see that many times you come up with milk, because you have the white, it might go with milk, and it's drinking, so you just mix everything together, and this might be some very simple, I don't know, like psychology of the grush, I don't know how to say it, but this is a very simple way to illustrate that indeed we think in this way. We think in concepts, and before we decide what words to mention, many times we think in concepts. And there you do much more sophisticated ways to evaluate the model and how this model fits better than other models. But this is the story. And I'm not going to go the direction as I promised you. I'm going to go the direction of machine learning and what we do it in, how we use it in machine learning. So first of all, there's the real challenge here is to infer what are phi, theta, z given a set of words. And mathematically, this is a challenge, and you cannot do it.
What are the phi, theta?
Yes, and also z. You might want to know what is the hidden topic, the particular hidden topic. So there's no one z, of course. So you can ask what is the most likely z, or what is the margin, and what is the distribution of z. But this might be interesting. And there are a lot of real-world applications that has to do with it, and I'll show you later on. I mean, the whole point of bringing something from IBM is to fit the real world. So I'm going to give you a taste of that in many of the other slides. But before we go there, let's just think for a minute about the mathematics that is behind this model. And the mathematical challenge is that you want to be able to infer these random variables, and it's no longer that simple as we had before. You just observe the words and you can find the likelihood. Here it's much more complex, and there are gift sampling, the rational inference. There are a number of ways to approach this challenge of how to infer the random variables, and of course, as soon as you infer them, you can say a lot about the documents. For instance, you look at a collection of 2,000 documents, and then immediately you can say, okay, they are talking about 10 topics, and here these are the documents that are mostly focused on this topic, and these are on that topic, and you can suggest referees this way, or reviewers. And actually, I know that in NIPS, I think that was held last 3 months ago, people use these models in order to try to infer who is the right reviewer. It was from Canada, from Toronto. The head of the NIPS this year was, forgot his name, המנחה של עמית. I lost it. Doesn't really matter. But the whole point is that it's being used. This model is being used in many different ways. I also will show ways that it's being used in IBM. I mean, I can't really share everything, but a little bit of it. So this is one example, the Innovation Jam. It will come in some other slide. The IBM model was that I just showed you and we went through was introduced in 2003. Since then, there were a lot of other models that are related that this work triggers. And one of them is the question: when you have a combination of authors on a document, you would like to ask, can you infer the connection between the topics and the words that you see and the authors that wrote the paper? And of course, if there was one author a single author for each paper, it would have been easy, because then you can infer this theta, this distribution of our topics per author. But typically, in our type of writing, we have a number of authors, so this entanglement to find who wrote what, who is interested in what, it's a challenge. And we came up with a model that assumes that each author has its own mixture of topics. And when someone writes a word in the document, it's picked from a topic and from a particular author. So, of course, we work together. We are very great collaborators. But we decide, okay, that's your topic. You are interested in physics or, I don't know, free will or whatever. You are going to write about that. And I'm interested in inference, in mathematics, and probabilistic models. I'm going to write about that, although we write together. And this is an assumption of the model, and immediately translates into a generative model that you see here, that assume, and again the same notation. You have these words, these observed authors, and it's a set of authors per document. And from this set of authors, for each word, a particular author is selected. This particular author selects the particular topic from the distribution of topics of that author, and then the word is selected. So it's a straightforward extension of what was carried out in the LDL, and it provides some interesting results. So I'm going to share with you some of the results just to give you a taste of what we do with this. Okay. Yes, it appears that you can generate documents using this generative model. Don't try it. I don't recommend it. I mean, you can write documents, the papers. I don't know if it's going to get accepted. For the subset, so do you know what size theory is? Who here heard about size theory? You know what I'm talking about? Size theory. Size theory is written somewhere. Size theory. Everybody knows that? I think maybe the right question is to raise your hand if you have never heard about size theory. Okay, young people. Okay, it's okay. You have other places where papers are stored, but at some point it was one of the best places that accumulated papers from online and put them in one place. And mostly computer scientists? Okay, so it's not young people, it's those neuroscience people.
No, neuroscience are not there. Mostly computer science.
Actually, we will see the topics in a minute. I just don't recall everything because I did it a long time ago. But we collected this is the work that I did with my colleagues in UCL when I did my postdoc. We collected a subset of more than 100,000 different documents, and actually it was mostly the abstracts because we picked the first part. It was hard to extract the words because most of these were PDF data, and these are documents from 1990 to 2002. And we wanted to use our orthotopic model where you have connections between, you have the model assuming how a document is generated when you have set of authors and so on, and to apply to these models. And after you apply them, and this is just information about how many documents we had per, this is the number of words, a number of documents that we had per year. And now we wanted to apply them. Don't ask me what the bars and what is the line, but it's more or less the same thing. So we wanted to ask ourselves, okay, given this large set of documents, we now observe the words, we observe the authors, we can infer, assuming a model, we can infer the topics, and we can count how many words per topic are used in each year. And this gives you, this is an evaluation of the model, I'm not going to get into it, but when you count how many words you have per year, it gives you some interesting insight about declining topics. So these words are the most probable words per topic, because what does a topic mean? A topic means a probability distribution of a word. So I can pick those words that are most probable, and then you get an idea of what the topic is. And the same for authors. I mean, if you are very familiar with these authors, I just give you the list of these authors, and you infer what the topic is, of course. So the topic is, in our model, is both. It's a set of authors and topics. And you can see that storage was not a very, memory cache was not a very interesting topic, and other topics. Let's see, other topics, I mean, you have other topics where you saw clear rise of this topic, like classifiers and data mining. And of course, I have an agenda here because data mining is what my team is doing, and regression, variance, and so on. So we can infer, you can look at a collection of documents and draw insights and understand what's going on in this community using this model. And probabilistic Bayesian models, again, I'm biased, I know. This was a very clear increased interest in this topic. So these are examples of one model, and I think due to the limitation of time, I'm going to skip the other interesting, nice models, and everything appears in papers. And I'm going to get to the IBM aspect just to give you a taste of what we do. And we do so many things, truly, that I can't really, it's not a taste of what we do. It's a taste of one aspect of one direction, because we do many different things, but this one aspect is there's a team actually that sits in Jerusalem that was Banter, iFirst, there's a long story, and then became IBM. So this is a startup that was acquired by IBM. And they have a classification technology for supervised learning, and we provided them with this approach, implemented, suggested, tested. There are a lot of technical, real-world questions when you want to make it part of an offering of a company, but we suggested them with this approach, and we actually came up with a more advanced approach that assumes you want to infer topics, but when you come to a customer, a real customer, and you say, okay, it has Bayesian, modeling, probabilistic, guess what the topic is? The customer will not be very happy. They want to have like titles automatically for their folders in their emails, for instance. They want you to take all the emails, analyze them, and come up with suggestions for titles for the folders. You can't really give this list of words. So what we did, we worked with another team within IBM that is familiar with information retrieval, and they had a copy of Wikipedia internally in IBM, the free version that everybody can download. And they used this copy in order to infer what is the best topic, because Wikipedia has categories. So if you have a topic of words, you can query, ask Wikipedia what is the best topic, and come up with the results. Actually, I didn't put in this presentation, but I think the most interesting story is that their technology that has to do with information retrieval has been used in the U.S. in a very, in the U.S. content. There's a show, a TV show called Jeopardy. Have anybody heard about Jeopardy? Okay, so some people know about it. Jeopardy, well, it's so challenging for me as not a native English speaker. You sit there and there are questions, and you need to infer who is the person or what's behind the story. It's a very very mysterious set of words, and you try to infer the connections between them. There are many. It's like trivia, but very advanced trivia. And IBM decided that they want to compete in this content. So they created a system that can infer, actually answer questions, very open questions, answer these questions with an automatic system. And they use this information retrieval and use Wikipedia, and they trained their models with Wikipedia. And there was and I don't recall the actual details, so don't catch me on that, but there was a rehearsal with two of the best, most succeeded in Jeopardy over the last, I don't recall how many years they have this show. It's America, they have shows forever, and they repeat it again and again. So there are these people who really won every year, or those that won, and the winner gets $1 million. So there are some people, I think there was a person who got 17 million, repeatedly winning so many times. So these are genius people in this content, they can connect the world, understand, know a lot about history, about nowadays sports, about medicine, about many things. I mean, it's really. And these people had a contest against a machine, and the rule of the game was that you can't really consult outside. So there's a huge machine standing as part of the show, and this machine answers the questions, and they are coming up with questions, and it wasn't obvious at the beginning at all, but at the end, after a very close competition, IBM won the Jeopardy, and it was at the end of January, I think. And one of these was using this information. One of the components was using this information retrieval. Other components were using analysis of text with many ways, rule-based, not rule-based, automatic. So there are many. So this is it reminded me. To take you to a different story. It reminded me this Jeopardy where IBM won the $1 million. Of course, they contributed it. We use the LDA model when there's in IBM there's some program called Innovation Jam. It happens every now and then. I don't recall it every second year, every third year, I don't know. But the idea is that people around the world, the globe, are welcome to put ideas of what innovation means to you, how do you want to innovate, and so on. And the IBMers are approaching the faculties and customers, and there were 30,000. These are the number of posts that we had after 2 days of this innovation jam. It's like some kind of a blog. Everybody can put his own stuff. And we used this method of automatic learning with LDA and then labeling it to infer what are the topics that people were interested in. So this was used internally by IBM in order to understand what's going on, what the 30,000 different posts were about. So these are the teams that I worked with So you have the paper of 2003 LDA paper. The orthotopic model is with Smith and Mark Steyvers and two other colleagues, forgive me. And the hypertext was with Amit and Yair Weiss and Amit Gruber. And this another paper that was with Amit Gruber and Yair Weiss too. So we carried out some studies in this direction. And this is my team, and we are doing many other applications in healthcare, in analyzing machine learning, many different things. Some of the people I guess you know from here. You have the pictures just to enjoy. Thank you very much.
Other questions?
Yes.
Most times the limitations very large corpuses.
Yes, it's a very good question. I mean, it's fair enough.
Could you repeat the question?
The question was, what are the limitations of this approach? I mean, when does it fit in, I guess in practice? Yes.
How does it compare to other systems? What is there any provable property of this system versus anything else?
Of course, it's debatable how to prove it and so on. So I'll start with the practical question. When you want to use this model for a very large corpora, like tera of memory or millions of documents, and we try to do it, you face, of course, a lot of challenges in the practical of how quick does it work, and you need to iterate when you try to infer the topics that are behind. You need to iterate a lot. It's a complex model. There are other approaches like information bottleneck that does clustering that might be much more efficient in the way that you infer relations, because it has less number of parameters. So there's always there needs to be the balance between the complexity of the model and the number of parameters that you use and the quick or efficient algorithm that you get. But since it was a big hit in the LDA model that was presented in 2003, there were so many papers around it that are papers on how to improve on this aspect and how to improve on that aspect. So I can't tell you from my own experience that we addressed all the challenges and everything works perfect, but there are many papers that having this message that there are ways to circumvent the problems of efficiency of the algorithm. This is one problem. To circumvent the problem of how many topics to assume, because it's a key question here, and it's a problem. So there are ways to circumvent them. I mean, they are not necessarily the best one, but there are always, in all these clustering methods, there will be such a problem of how many clusters to use. So I don't think it's particular to this model, but it's also a very big question how many clusters to assume in advance, how many topics. And it's being used and shown as valuable in many different ways, like inferring spam. When you have emails, you have recipients and the senders, and you can find connections between them and the content, and then you can infer spam. When you compare it to something that goes by the rule and says if the words, dirty words appear, all kinds of things, then it's spam. Many times this rule-based approach is much better. But then there are also, of course, models that suggest combining the rules with the statistics, and there are ways to combine them. So there's a large body of work following these models, and I can say that efficiency is one limitation, number of clusters another limitation of the model, and it's not easy. I mean, when you try to do research and you try to suggest other models, you have a long way between the model you suggest and the actual testing of how well it works. Because as soon as you propose a new model, you have to come up with a new inference approach, a new mathematical, and then a new algorithm, and then to test it. So there's a long way. And this is one of the reasons each time you have a new model that succeeds, you have a paper, many times, maybe 10. But also it takes a long time to evaluate it. And I don't know, I guess you can answer your own question about how well it performs against.
We talked about it many times.
Yes.
There are two main limitations. First of all, it's a generative model. It's not unlike other methods which are sometimes independent of the statistics of the data. Here you actually assume something about the way documents are generated, which is not entirely realistic.
I didn't hide it under the rug. I said it out loud.
It's as good at most as the connection between the model and the true data. Now, at the same time, it's efficient because you're using the machinery of Bayesian graphical models and many good ways of doing it. But even then, the hidden variable models, so you have the EM essentially as background.
Not always.
Not always.
Git sampling, variational inference, mean
all
field.
the difficulties of hidden variable models that are.
Yeah.
So essentially, I don't know, what makes it a winner is mainly the fact that you push it all the way to
get results.
To get results.
And if you get good results and you evaluate the predictive power, then sometimes it works well.
The scientific value of this, I think, is a question.
So as
the model was generated. You always said that it was invented in 2003. It's really not true. It was there at least 10 years earlier.
Yeah, but I also said it's not true, didn't I? I said. Yes.
I'm still confused about the structure. So you have in inference to use to given a set of words, what are the topics and so on, what are the random variables, what are the likelihoods of them, right? But what are the parameters of the model?
Yes, it's a good question.
You said the number of clusters, so there's obviously one parameter.
Yes.
It's the Dirichlet process.
Yeah,
it's
a good question. The parameters are well defined here. They are called the number of clusters is parameter, and the number of document number. So all these letters represent something that are parameters, something to be inferred.
The number of documents.
It's given. You don't need to infer. You don't talk about it only, but you still a parameter over there.
Okay.
So, but these two are called hyperparameters. They are called hyperparameters because you have to fix a value for them. You don't have any prior over them.
Right. So those are the priors, right?
Yes.
Prior parts. So these are. So how many parameters of that nature you have?
I mean, it's clear. I mean, if you have, first of all, these hyperparameters, these priors, they are fixed. They are called semantic priors, so they are fixed to have one value, although it's supposed to be a vector. You have a prior per entry. So if here you have a vector of the size of the words, the multinomial is the size of the words, you can have a prior.
The size of the word.
The size of the vocabulary. The size of the vocabulary is supposed to, so phi is the size of the vocabulary, and probability for each word given so. And you have t size.
So this vector of probabilities is one parameter.
So this one was supposed to be the size of the vocabulary, but it shrink it to one parameter in this model. It was supposed to be this is a vector, and the size of this vector and this vector are the same. It was supposed to be beta 1 to beta b, that's some number, but you shrink it to 1. So you have one here, and t here, which is the number of topics.
But phi still is a vector of phi probabilities over the words.
Yes, but phi is already a random parameter. It's another parameter because you have a prior for it. So it's picked at random. This is not a parameter.
What?
This phi here is not a parameter.
That's a parameter.
No, it's a random parameter.
But the probabilities of this random.
So
you have some frequencies of words. You have some priors about frequencies of words and in language. Or
so you treat it. Yes, you say. Let's say the way I explain it to people who just get into the area, I say, let's think about a coin. When you flip a coin and it's biased, you can say you can infer the bias and then it's a parameter. But let's say that you pick from a pile that all these coins are biased, and somebody randomly picks the bias and puts some coins that are biased. Now you pick at random a coin, it is biased, and you can infer the bias, but this is a random variable. The bias itself is a random variable. And you have some prior of this random variable. So the same here. This is some biases of the word application. It's a random variable and you infer it. It's not a parameter.
So you have 5 parameters, 10 parameters.
I have 2 parameters here and another t. So it's 3 parameters. That's all. And the rest
the entire big.
Yeah, it's the whole point of Bayesian models. It's going away from parameters. I mean, everything is random variable here. It's a generative model that is a hierarchical Bayesian model. So that's the whole point. But people are also not, as Sally indicated in principle, people are not very pleased with having even these parameters. So there are ways to avoid having this trial. And there are these
Total story. 3 total.
No, it's not topic. There are 3. The rest is random variable that we
But you have
infer.
structures in the distribution. The distributions are not
the distribution are not parameters. These are random variables that you infer.
But the distributions are random?
Yes. Like the bias in the current in this time.
So,
And if the Dirichlet processes that have parameters.
No, the Dirichlet process. This is the Dirichlet prior. This is not the Dirichlet prior. The Dirichlet prior essentially should have had beta and beta of size V, so V different parameters, and the assumption is that they are all the same.
what is
V is the vocabulary term.
so each one is IID. So what?
But maybe I think that everybody, I
Well,
mean, this
it's
is
the same.
thank you very much. We can have this.
I'm very impressed. Okay, very good.
Okay. So we can thank the speakers.